Welcome to Math 31. This is a lesson on tangents and secants, which is the first lesson in the limits unit. So this gives us some necessary background into limits before we're able to go deeper and go further into that concept. Tangents, you would have seen this before earlier, probably Math 20. But a tangent line is a line that touches a curve in only one place. Now that's not a perfect textbook definition. However, it does, geometrically, it works well for us. It gives us an idea of what we're talking about. So it's good enough for me now. And if you take a look at this circle we've got, this would be a tangent line. And it comes into contact, say, right there, which we would call the point of tangency. If you work with circles a lot, of course, you're aware that that tangent is perpendicular to the radius, and that there would be an infinite number of those tangent lines around that circle. That's not really what I'm concerned with here so much, just the concept that it's just touching it in one place. Same thing would be true if you had a cubic function, say like this, and you could draw as many as you wanted, but this would be this line is tangent to the curve at that point only. Now, before we go further with this, some information. Why this is significant is, if you think to physics courses, or even very simple sort of science programs where they work with distance-time graphs, or even more complicated matters in physics particularly, you're dealing with the slope frequently. So you'll have the rise over the run of a distance-time graph giving you speed. We use that a lot. And then the slope of a speed time graph is acceleration. So some of you know what I'm talking about with that. Now that's great, except that only works well when you're dealing with linear graphs. And if your graph is not linear, then you run into this problem. I want the slope, but how do I calculate the slope, which is really a linear measure, when it's not a linear graph? So this is where we start dealing with one of the fundamental questions of calculus. How can we determine what the slope of a curved line is, say, at a specific point, or even better, a formula that will work for all points on the curve? And it begins with this. Now this is eyeballing it. I drew those in there just by roughing it in. And that's actually a fairly good method, but it's not good enough if we really need this for better calculations. So, if we look at this ellipse, and if I drew say, a line like this that is cutting the curve in two places, we call it a secant line. So it's distinguishable from a tangent line in that it comes into contact in two places. Then, if I want to use, if you think about it like this, if I want to use that secant line to approximate a tangent at a specific point, I could. Because a secant line has 2 points, and in order to calculate the slope, you do need 2 points, right? The formula is based on that. So the trick is to make that secant line get closer and make the second point of the secant line, say this one, closer and closer to this one. So let's take a look at the next illustration. Oops, back her up. Sorry about that. If we looked at this, and if we wanted to get the slope of the tangent line at point P, what I could do, draw in a secant PQ. Now, I'm going to do a very poor job of selection. I picked point Q1 right there. And I want to use the slope of this, which I can calculate using those 2 points, to approximate the slope of the tangent line at P. Now, I'm doing a bad job of it because Q1 is so far away. So I would then pick a better point, Q2. Now, that's a better, but still, Q3 is better. And in fact, you could keep doing as many as you wanted, and eventually you would get a better approximation of it. So the lesson here is that the limiting slope of the secant line PQ, as Q gets closer to P, is going to represent the slope of the tangent line at P. So if you were to Armstrong your way through this, just do it. If somebody gave you a ruler, an equation, and the graph, and said, get me the slope of the tangent line at that point, you might be inclined to do this. You'd pick a point Q closer and closer until you got a good approximation. Not a very good method in the sense that it's very time consuming, but in fact it's fairly reliable. So let's take a look at this one. F at x is equal to x squared, just your regular quadratic. And if we were to determine the slope of the tangent line at x equal 2, we could. Now, I just noticed that these y values are like totally wrong. So if we wanted to get the slope at x equal 2, we should be able to do that. And how I'm going to do it is the Armstrong method that we just looked at previously. I'm going to find my x equal 2, and right here, and I'm going to call that point P. And point P has x is equal to 2, and if you use the equation to find y, 2 squared is 4. So the y coordinate is 4. And if you selected values of q that were close, now I'm going to play dumb with this one. First off, I'm going to call this q1. X is 3, and y is 3 squared is 9. So the slope of PQ1 is equal to y2 minus y1. So I'm going to go, I'll write that down this time, y2 minus y1 over x2 minus x1. And therefore MPQ1 is equal to 9 minus 4 over 3 minus 2. Work that out. 5 over 1, the slope is equal to 5. Now that's a poor approximation. Now I'm not going to bore you forever doing this, but I'm going to pick another point, Q2, that's closer. So let's get quite a bit closer. Q2 is, let's say, 2.1. And then, in order to get the y coordinate, you have to plug in 2.1 into that x squared formula. So 2.1 squared is 4.41. So now if we want to get the slope of PQ2, it would be equal to subtracting the y coordinates, 4.41 minus 4, all over top of 2.1 minus 2. And that gives us a slope PQ2 is equal to 4.1. Now we could do this a lot. We could keep selecting points Q3, 4, closer, and the approximation would get better and better. But I'm going to stop right there, and I'm going to say by inspection, and I'm taking a leap here, but I started at 5, I got 4.1, I wrote this 4.01, it's actually 4.1, I don't know what I said. By inspection, the slope appears to be 4. So you could try it. If you went x is equal to 2.01, you would in fact find, if you calculate the slope, you get 4.01. And so on like that. It would get closer and closer and closer to 4. The method works if you have the equation. You can just keep substituting numbers in. It's a total Armstrong method for doing it, though. So the next question would be to do that algebraically. And the method algebraically, you're going to be seeing a lot of this in the next while. In fact, this will eventually transform into what they call the first principles method of calculating the derivative. So this is a bit of a foreshadowing of a very major topic in the course. Now once again, I'll pick x for point P, x is 2 and y is 4. And when I say do it algebraically, I mean I'm not going to be substituting in additional x values that are closer and closer. I'm going to work under the principle that I want to make my choice for q as close to p as possible. And I'm going to call this h the horizontal distance between P and Q. And then, so there's point Q, I'm going to come up with the ordered pair for Q. Now be careful. The x value for point Q is 2 plus h, because we've added on h to the original point 2. And then, because f at x is equal to x squared, this would mean that f at 2 plus h is equal to 2 plus h squared. So it looks like that. So that would be the y value, whatever h was. Keeping in mind down the road, we want to make h as small as possible. So now when we calculate the slope of PQ, we just substitute it in. y2 minus y1 is 2 plus h all squared minus 4 all divided by the x coordinates. So 2 plus h minus 2. So m of PQ is equal to, now if you expand that 2 plus h, you get 4 plus 4h plus h squared minus 4, and then the denominator would be h. 2 plus h minus 2. And then our 4's will subtract away. And if you're really on the ball, you'll see that by factoring an h out from both of those terms on the numerator, we get 4 plus h, all divided by h. And we finally get the break we've been looking for, because now we can divide by that factor of h, and we're left with MPQ, the slope, is going to be whatever h is plus 4. And then we recall that as the h gets smaller, approaches 0, I'll just write that like that, the slope of PQ approaches 4 plus 0 is 4. So therefore, the slope of the tangent line approaches 4. So that's important. That's a big deal. It means that we have calculated what the slope is. And it isn't a quick method, and we would definitely make it go faster in the future. But the principle behind it is very foundational, if you like, to this particular unit, or in this course that we're taking. Let's do the same thing here with a more complicated equation. F at x is equal to 4 minus x squared at negative 1 comma 3. So that's going to be right about there. So I'll do the same thing. I'll go point P is negative 1 comma 3, and then I will note that h would be the value somewhere. You could move this to the left if you wanted. It really doesn't matter. But I'll go to the right just so it's clear that it's a positive value. So our x coordinate is negative 1 plus h. Our y, now be careful, because f at negative 1 plus h is equal to 4 minus negative 1 plus h all squared. And that's what we get, 4 minus negative 1 plus h squared. And now all we do is get the slope of PQ. Now when I'm getting the slope of PQ, keeping in mind that ultimately I want this to be, I want this to be with h is approaching 0, I am really trying to find out an approximation of the slope of the tangent line at point P. Now keep in mind as well that I'm not saying h is equal to 0, I'm saying h approaches 0. So in order to get the slope, we do need 2 points. You can't just have the 1 point, but we want those 2 points to be as close together as possible. So moving on, we get 4 minus, subtract the y coordinates, negative 1 plus h squared, minus the y coordinate of 3, all divided by the negative 1 plus h minus negative 1. I'll put brackets around that numerator. You don't really need them, but I'll keep it clean for now. So we go on. This turns into 4 minus, when you expand negative 1 plus h, you get 1, positive 1, minus 2h plus h squared. And then this is minus 3. The denominator, negative 1 plus h plus 1, will leave you with h again. So we go on. MPQ. Do not make mistakes on this simplification. And you get 4 minus 1 plus 2h minus h squared, and then minus 3 all over h. And once more, we get some simplifications on the numerator. 4 minus 1 is 3 minus 3. It's gone. So MPQ is equal to, we factor out an h, and we get 2 minus h divided by h. And we're able to divide out that factor of h from them both. So MPQ is equal to 2 minus h. So that's a formula that will work for all values of h. But what we want is this again. As h gets smaller and smaller, so it approaches 0, MPQ approaches, the slope of that secant approaches 2 minus 0, 2. So therefore, the slope, get rid of that, of the tangent line at x equal negative 1 is 2. Now, that's a bold statement because I'm essentially saying that it's no longer an approximation. I'm saying that it is that is what the slope of the tangent line is. So we want to be a little bit careful with that. I'm comfortable saying that. In fact, that's what we'll use it in the future. But you want to be aware that the actual development of this is based on an approximation where the points are getting closer and closer together. So it really, really, really is an approximation. I'm just going to do one other thing with this. You often will get questions like this. Find the equation of the tangent line at x equal negative 1. So don't forget that you may have to do this. It's not a big deal. We know, according to our calculation, that m is equal to 2, and we know it's passing through the point negative 1, 3. So if you used y is equal to mx plus b, you should be able to work it out. Y is 3, m is 2, x is negative 1, and then b. So b is equal to 5. So the equation, therefore, is y is equal to 2x plus 5. If you want to have a quick look to see whether that seems reasonable or not, go back to the graph. And here's 5. It's a little messy up here, but I think we can sort of work our way through this. And if you drew the line, see if I can draw that. Don't have a very good ruler with this. Yeah, that's not a very good one. Oh, boy, I shouldn't even have started this. Can I do it? Ah, there we go. So forget about this guy there, or this one here. And yeah, that's not bad. That looks like that could be the tangent line there. So that's how that works. Now the next lesson we'll be working on the limit proper, introducing the notation and stepping away from this for a little while, and then it gets reintroduced deeper later in the unit. Thank you for your time.